Welcome back. So this video is about the last combinational circuit that we'll be designing in this course, and that goes by the name of the digital comparator. It basically is a circuit which has two inputs, like here it is A and B, and it actually compares the two inputs. Fine, so A is binary, B is a binary number, and based on the comparison, you can actually have three outputs. First, if the two numbers are equal, as A is equivalent to B, so in that case, let's call it, say, F equal output. And A less than B, so let's call it F less than, or you can have A greater than B, so let's call that output FGT, right? So you can have one of the three possibilities. Either number A will be equivalent to B, or it will be less than B, or it will be greater than B. So it's basically a comparison circuit which compares two numbers. Fine. So a digital comparator, yeah, let me write it here. What it does, a digital comparator it takes two numbers for comparison and generates one of the three outputs. Fine, and the three outs can be greater than, less than, or equal to. Fine. So what we'll be designing in this course is a 2-bit digital comparator, which actually means that A will be a 2-bit number, A1, A0. Similarly, B will be a 2-bit number, B1, B0. And again, we'll be relying on the general methodology, wherein these are the variables that we have worked out. These are my input variables. So they are 4 in number. And then we have three output variables depending upon what the value of these numbers is. So we have three output variables. The next step is we have to establish a relationship between the input and the output variables. And for that, we need to construct a truth table. So here is a truth table. So what we'll be doing is that we will keep, for example, A1 and A0, will keep it constant, let's say at 0, 0. And then list the different combinations of the other input. It can be 0, 0, 0, 1, 1, 0, 1, 1. Now for the first case where you compare 0, 0 with 0, 0, and we'll have three outputs, F equal, F less than, F greater than. So for the first combination, A1, A0 is 0, 0, B1, B0 is 0, 0. So in that case, it is equal. So this will be 1, 0, 0. And when you compare this 0, 0 with 0, 1, it is less than. A is less than B. So F less than F, this output will be high. The other two will be low. And you compare 0, 0 with 1, 0. Again, A is less than B. So this output will go high. The other two 0. Again, comparing 0, 0 with 1, 1. A is less than B. Then we'll take the second entry of the input A, 0, 1, and again compare it with 4 values that the B can take. And for every comparison, we will list whether it's equal than, less than, and greater than. For example, the first entry here, 0, 1, is greater than 0, 0. So it will be 1 here, 0, 0. And again, 0, 1, comparing with the second entry, 0, 1, it will be equal, will be high, these two will be 0. Then 0, 1 compared with 1, 0, it is, because 0, 1 is less than 1, 0, so we will have F less than high, these two 0. And finally, for the final entry, again, A is less than B because 0, 1 is less than 1, 1, and low. Fine. Then the third combination is 1, 0. Again, we will compare it with the 4 combinations of input B. First combination 1, 0 is greater than 0, 0. So this will go high. Other two will be low. 1, 0 again is greater than 0, 1. So this will go high. these two low. 1 0 is equal to 1 0, so this will go high, 0 0. Then 1 0 is less than 1 1, this will go high, other two 0. Finally, the last combination for A is 1 1. Again, we'll compare it with the four different combinations of input B, and based on this comparison, you can see it is greater than here, again greater than for the second combination, and equal for the last combination. So this is the way we actually, what you call, establish the relationship between the input and the output variable. So we have four input variables, A1, A0, B1, B0, and three output variables, F equal, F less than, and F greater than. Fine. So in terms of min terms, this first combination, so this will be min term 0, min term 1, min term 2, min term 3, and min term 4, 5, 6, 7. So there will be 16 min terms, 11, 12, 13, 14, and 15. Then we'll come up with the expression for each, F equal, F less than, F greater than, based on where this particular output is high. So F equal is high here, M0, M5, M10, M15. F less than, M1, M2, M3, then M6, M7, then M11. Likewise, F greater than is M4, 8, 9, 12, 13, and 14. So we'll get Boolean expressions for F equal, like I have listed it here. F equal, F less than, so F equal, F less than, and F greater than. Then we'll try to minimize them again using the K-map. I have a 4-variable K-map here. Let me just see if I can separate it out. Yeah, anyways, it is fine. So for the first one, F equal, we will have entries like this: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I have ones along the diagram, and obviously they cannot be combined. So this means F equal is already in its simplest form. It cannot be simplified further. Now let's try out for F less than. So we'll do one thing, we'll use the same K-map just to save some time. So for F less than, I have min term 1, so this is 0, this is 1, this is 2, this is 3. Then we have 4 is not there, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. They are not part of this. So we can change to work out combinations. For example, I can have one combination. I can have a chord like this. So this will be 1. Then I guess another chord is not possible, so maybe we can have some other combination. Let's say like this, 2 here. And then I can actually combine them, one from this and one from this, right? So using these combinations, you'll come up with a simplified expression for F less than output, and it will be corresponding to the chord. It will be A1 complement B1. Then for the two adjacency, I will have A1 complement A0 complement B0, and then the third term will be A0 complement B1 B0. Fine. Likewise, if you go for F greater than, so let's have a map here. Let's have this map. Again, it will be A1 complement A0 complement A1 complement A0. This is actually the usual processor, because we are aiming at implementation using gates. If you want to implement it using multiplexers, so multiplexers have an advantage. You don't actually need to simplify the expressions. So you can also try it using multiplexers, wherein you don't need to simplify. You just have to choose a proper multiplexer to implement it. Fine, like this. Fine. So let's see how we fill this up. So as you can see, I have terms 4, 8, 9, 12, 13, 14. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's just 12, 13, and 14. Let's just see. Okay, so it will be 12, 13, and then 14 will be here. 15 is not there. So we have 1, 2, 3, 4, 5, 6. 1, 2. Okay. Then again, you can simplify it. This maybe if you can see there is a chord visible. Let me work it out. So this is my chord. Then another chord will not be possible. So again, we look for two adjacency. Say two adjacency like this. Then another two adjacency like this. Fine. And based on this, we can come up with the equation for greater than. As far as chord is concerned, I will have A1 dot B1 complement. For this yellow one, it will be simply A0, then B1 complement, B0 complement. And for the black combination, it will be A1, A0, B0 complement. Fine. Then you can implement this using, because it's an SOP form, so you can implement it using the and or realization, or then later on you can convert into NAND. Those things we have done, we have done it multiple times. I hope you can actually implement it. So this is a 2-bit comparator. Fine. If we go for a 3-bit comparator, you will have inputs A2, A1, A0 representing the input A, and then the bits B2, B1, B0 representing the input B. So in total, you will have 6 input variables and 3 output variables. So you can actually draw a truth. It will be a larger truth table, but problem is that you can't solve it using K-map, because K-map we only use up to five variable, right? So you may then directly implement it using a multiplexer, right? So this was the last combination circuit that was a part of your course, the digital comparator, right? So let's stop here.